Hello, this is working. Okay, so this time I'll show you how to create a figure like this one. So this one is the an open-ended tile, which you can see here, capturing or coring some material that's rising above the mud line due to the latency, and the everything is colored by well the displacement gradient as an absolute value, while vectors are also plotted on top, so you can see the direction of these movements. But since the size of the vectors is always the same, you can doesn't get obscured by their intensity due to the background colors. And well, this is another example, but with plugging, so material is going downward, and you have the displacement is there is higher friction here, and the displacement is consistent for a larger portion of the material inside the pile. So this is the file. I already loaded the mesh data as done in the second video or one of the previous videos. What I'm doing here is also creating an output video with using the video writer function, just decide the duration. The frame rate is just length of results divided by time, rounded down, and therefore you get the frame rate. Open the video, and then this is carried out for every step of the simulation. You get the elements and the nodes. As done previously, it creates the scattered interpolant, ds and dy, which I ended up actually not using, but you can do something similar, or you can do basically the vector plot by calculating the scattered interpolant of the displacement along x and y, and then evaluating it along a grid, so you get a grid of displacement. So let's just continue here. Creating the scattered interpolants, the x and the y. Let's say we have mesh is equal to mesh grid from 0 to 1. Let's see the previous image, for example this one, from 0 to 1, and we want 100 of them, so increment of 1. And then the same for y, we want from -3 to 0. This will create xx, yy, which is the two maps. And then you can do scattered interpolant dx in xx. I don't think this works straight up, or maybe it does. Yes, it does. So this close all IH or contour should be more or less homogeneous because it's the very beginning. Yeah. So this is would be the result. Instead of doing, so I created an interpolation matrix and obtained all the values across the entire area at the very beginning, where you have some portion of the material moving left and some moving right. And if I just do vector dx, I can do to reshape, change the shape of this matrix to numel, so column multiplied by rows, and 1. Well, let me just do the same with a map for the y, so you can get the displacement on y. Oop. And then you can do no, you can Weaver, so the 2D vector plot. Map. Let's see if we can just do it directly. Map dx, map dy. I don't know if this will work. Oh, it does. Yeah, it looks like garbage, but it does work. And you can see here that near the, if I zoom further, near the point where the pi is connecting, it's plotting the arrows. Let's say Weaver scale 10 maybe. What was it? Weaver. Come on, autocomplete. Scale 10. Well, I don't actually know how to do autocomplete on Quiver, but you can see this. Maybe I can just write 10 or 05 and we'll make everything on that side. Maybe. Nope. Well, this is what you get. Just the Quiver plot. In this case, we're not going to use the X and this method, which will work because since we are creating a mesh grid, and for example here we don't have data, you can either decide to extrapolate and therefore you have data that doesn't exist, or since if you don't extrapolate, it calculates the data within a convex hull, so this area will still be filled with data, which is something we don't want. So here I'm going to do something different for the Quiver plot at least, so we can just comment this out. What I do is, instead of doing the x and the y, since I don't care about the modulus of deformation, but just the angles to plot this vector, is I'm calculating a vector of angles, which is the arctangent of the ratio of the y on the x. So this vector, then I calculate the arctangent in degrees, and then what I do is, instead of plotting the vectors, so you can see here that the vectors are more or less equally spaced, but you can also kind of see that they're not explicitly placed on a grid. They can have more holes or more distances, and the reason why is this is, instead of defining them as a grid per se, I'm taking the nodes of the mesh, x and y, I'm treating it as a point cloud, so converting it to the point cloud format, setting the displacement of these points as normal of each point, so you have the cosine multiplied by size. So this doesn't matter, this is just the size I want each arrow to be, multiplied by the sine. So you cosine on x, sine on y, or minus sine because of the direction. People are throwing stuff at me again because sad people. And then since the original mesh will be too fine, I'm downsampling it in order to get a grid average, which means of size E, which means I get data point in the point cloud every thought distance, so I get something very uniformly sampled, like here, and then I just reconvert backward from point cloud to a data set I can actually use. So I get xy, which is the location, and normal is and xy is normal. I define a set of limits for the image. For example, the full model, I don't have Git open, but will be much larger than 1 meter large or wide, and much more, or goes much deeper. In this case, since we only care what happens around the pile itself, we are only showing the region. So what I'm doing is defining the region where I want stuff to be shown here, and then I define a color map. Very easy, probably my favorite color map because it increase the value also increases monotonically with the map, so it works very well even if it's converted to grayscale. And then what I'm doing here is plotting the background uniformed color value for what you can see here as displacement. How is it obtained? For every element, I get the 3 nodes. So element, if you remember the data format earlier, the first value is ID, and the second, third, fourth values are the node ID X, ID over 1, 2, 3, because it's a triangle. If it was a tetrahedron, would be 1, 2, 3, 4. And then what I do is check if any of the for each element, if any of these corners is within the region of interest. I calculate the displacement as just the well, the data already gives me on the fifth column, because it was ID X, Y, Z, so 4 plus 5 is modulus, so already have the modulus of displacement. For each of these nodes, and then I plot the triangle itself using the fill command, which means it's point 1, point 2, point 3, the 3 x's, the 3 y's, and the values, and then I just say line style now, so I don't have conjunction lines between the mesh elements. Let's just continue and see if the model cycles until here what we get. Oops. Okay. Just, um, unfortunately, I need to go step by step because I modified the code. So we are here. Let's see. We have an empty image. We plot one individual triangle, and this just repeats the step. For each triangle in the domain, the color scale is automatically updated. This goes on for every triangle. Oh yeah, I can step. It's gonna go back to here, I think. Yeah. In any case, just you get the color bar, or just define the color bar, which is the this bit. I plot. I give a label called displacement to the color bar. I plot the quiver as shown before, so x, y, dx, and y. And y as red vectors. Remove autoscale, so the side they're not scale by side. align vertex centers on, so they're more or less always centered in the same position for each one of them. I define the axis or set the axis of the figure, so x limit, y limit, and z axis limit, which means color scale limit. Let me just stop here, and transaction should run up to here. Yeah, sure, continue. Okay, let's just create another substep. Yes, so I created all the values. You can see here that the displacement is at the beginning very dishomogeneous, which is kind of weird, but let's just pretend it's not weird. Also, you can see the interdomain has been plotted. And then uh, by setting this contour, the color axis to from 0 to 0.5, all the values are rescaled in this dimension or this interval, which is very good for this specific occasion, because if the pile is inserted for 2 meters, the values of the displacement near the pile itself will be very close to 2 meters, and this masks or hides the deformation in the other regions. Like, this is basically just an outlier. What we care about is the distribution in the rest of the domain. And so this is why I set the color axis to this value, and that's about it. Oh, and then the next step was continue adding the pile. How is this done? Uh, you get maximum penetration depth from the time multiplied by the velocity, and then I just define a set of points for the pile, which is, let's just go with the image, which is easier, which is start or maximum position, minimum position, and then I just do cosine from, or do 10 points from minus 180 to 0 for sine and cosine, and get the curved bit at the bottom of the pile here, and then I chain up another displacement here, and so that's the pile itself. And then just set the labels, draw the thing just to show it here. And the next thing is, since as done earlier, we were creating a video here. We open the video. We need the figure to be converted to an image to save it in the video. So the way to do it is get frame, get current frame, and then frame to image, and you get it as a color scale, and just write to video. And after all the steps, close the video. And that's it. Bye bye. What's up?